you.
Andrew, I'll bring yours tomorrow. I didn't know you
Oh,
were in
is
this
it the
class.
final? Oh, no.
Yeah, I didn't know you were in this class too. I'll bring it.
No worries. Okay.
Yeah.
That person.
This is. This is. There's something to achieve.
So how do you? Probably not for so many seconds.
All right, it's 3 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? Good, good. I'm good. Thanks for asking. Good to meet you all. So welcome. This is EGME 410, Introduction to Finite Element Analysis. This is the start of section B, so will be together for the next 5 weeks. My name is Professor Justin Tran, and I will be your instructor. So Plan for today, it is changing a little bit. So first half of the class is not going to change. So, first half I have just these introduction slides just to introduce the course to you guys. We'll talk about the syllabus. We'll take a tour of the course website, just to kind of get all that introductory stuff out of the way. I did want to do the first ANSYS activity today as well, but it looks like there are some issues with the licensing server for ANSYS, and so which is not untypical, but of course, and I did test it last week, but of course today there's issues. So I did contact IT. I don't know if he's going to get back to me before the end of class today, but I did prepare a lecture for today as well in case that's not going to happen. But I think that issue should be solved by tomorrow, so we should be able to have our first ANSYS activity tomorrow. And I'll shift around the due dates as well, just so that it's not too much of a load. Okay. So I think for now, plan for today, just do the lecture, introductory lecture slides. And then we'll just have some lecture notes after that. Then we may be able to leave a little bit early from today as well. Okay. All right, but yeah, it'll be kind of a good session. I think there's only about 25 of us in the class, so I think that's really good for a class like this, just because that's a lot of it is going to be we'll be using the ANSYS software, and so this will kind of give me a good chance to kind of get around and kind of help people and talk to you guys about the product. All right, are there any questions I can answer before we get started for today? Okay, all right, so let's go and get started. Okay, so first, a little bit about myself. So my name is Professor Justin Tran. You may call me, whatever you feel comfortable with. And so I think a lot of people call me Professor Dr. Tran, but you can call me Justin as well. I like to still think that I'm still fairly young, but I think I can't really say that for that longer. I was just reminded over the weekend that I'm getting closer to 50 than I am to my high school graduation. So that was kind of a sobering thought about that. So my email address is there on the screen. So my email address is justran@fullerton.edu. I always like to joke with people that that I stole this email address from a running club that used to exist here at Fullerton, but that's just my name. I'm very local to here, so I grew up in Cyprus. If you're not sure where that is, that's just about 10 miles west on the 91. My entire schooling has been here in California, so I got my bachelor's from UCLA, my master's from UCSD, my PhD from Stanford, all in mechanical engineering. So I've been all up and down the California coast. My research interests involve applications of engineering tools to study biomedical problems, specifically finite elements. And so this class actually has a special kind of place in my heart, no pun intended, for a lot of the work that I do. So I'm very happy that I get to teach that here. And just as someone who teaches, engineering courses full time, I'm always interested in, how can we better do this and be more effective for you guys, for the students. Okay. Next we have our learning objectives, and so I know some of you probably have taken me before as an instructor, but so you're probably used to this. But this is something you'll see at the beginning, of course, of each lecture every day. So I like to list out what I call the learning objectives for the day. So just on a surface level, you can think of these as just kind of an outline in terms of what you can expect to learn for the day. And so, that's always good for organizing your notes. So I always encourage people to, when you're writing your notes for the day, especially when we have a lecture heavy day, we're not really doing anything with ANSYS, please write these down, just because they kind of help organize your notes, and you can just tell at a glance kind of what we did that day. Okay. But, if you kind of read my learning objectives, you'll see that I kind of write them very intentionally. So I start each and every one of these learning objectives with a verb. And the reason for that is that, each of these objectives describes a specific skill or specific piece of knowledge that, you should be able to demonstrate by the end of the class. Okay. So for instance, the first learning objective you see there is describe the use and utility of finite elements in engineering work. And so by the time you leave the class today, or by the time this introductory lecture slides are over, you should be able to do exactly that, right? So and if you're especially clever, you'll start to see that these make actually really good exam questions as well. So we only have one exam in this class. This class is mostly project based, but when we do get to that exam, the learning objectives I think are be good to pay attention to. Okay. So definitely write these down at the beginning of your notes. I'll have these up. Usually I try to come to class at least 15 minutes early, and so write these down and just to kind of help you prepare and just to know what to expect from the lecture today. Okay, All right, so first thing I want to discuss about the class is just defining what is finite element analysis. And so, so I've been teaching this class for a while now, so I think, I think some people kind of come in with certain expectations, but, I think just to make sure that everyone gets on the same page, let's define what that means, okay? So finite element analysis, just in general, is the numerical technique for solving differential equations on arbitrary geometries, which, may not sound kind of similar to what you're expecting. I think people think of this as the ANSYS class. But, finite elements goes way beyond just a particular software. In fact, actually, if you look out in the world, there are actually, dozens and dozens and dozens of softwares that implement finite elements. They're just in different software that, people try to sell, right? But as a method in general, it's a numerical technique for solving differential equations. And what I want to do today is to kind of form that connection between what it means to solve a differential equation and connect that to, I think, what people kind of understand from maybe what you've experienced before in SolidWorks to ANSYS to I would say kind of modern finite elements that we kind of know for okay. And the basic idea is that finite elements really leverages the ability for computers to perform mathematical arithmetic operations at speeds that are much, much faster than a human can do, okay? And so you'll see that, once we start to go over the theory behind finite elements, and you'll start to see how these finite element problems are set up from a mathematical computational standpoint, these problems are not designed, they're not really practical for humans to solve, but they're set up in a way so that computers can solve them much more easily, okay? And the way that finite elements is typically used in a modern engineering context is that it allows basically the design and analysis of engineering systems with very complicated geometry, very complicated loading, boundary conditions that just gotta go way beyond what you can do with hand calculations. Okay. So probably what you're used to up until this point in your engineering education, you've at least taken solid mechanics, so that prerequisite for this class. Some of you probably have also taken fluid mechanics, heat transfer, kinematics, courses like that, right? You're probably used to doing these hand calculations on problems that either have a lot of simplifying assumptions or they have very simple geometries. And while those types of problems have a place in engineering education, you have to learn the concept, you have to learn the basics. You hardly ever see any practical and any engineers out there in industry, using hand calculations on their very complex systems. You need the aid of some kind of computational tool. And finite elements is one of the most common ways for people to do it. Okay, so to kind of illustrate this further, when I think of engineering analysis, I think of kind of three broad categories of types of analysis that people generally do. Okay. So the first type is what I define to be analytical analysis. And so this is kind of the traditional pen and paper calculations that you would do in a typical kind of theory-based class. And so the idea with analytical methods is that you have a governing equation that you are assuming is going to govern your physical system of interest. You're going to solve that governing equation for the variables of interest, and you obtain some result. Okay. Now, the good thing with analytical methods is that it's very fast and inexpensive, right? And so pencil and paper is very, very cheap compared to an engineering rig or an engineering setup or even just a computer. But you're very limited into very, very simple problems just because it's very hard to add complexity to these pen and paper calculations. Okay. On the complete other side of the spectrum is what I define to be experimental methods, which would be, which would involve, actually testing out some kind of, physical situation and collecting measurements and data to learn more about the system. Okay. And I always say, the best way to kind of learn about a system is to just try it out and kind of observe and collect data and see what happens. Okay. Now, experimental data is always the best, right? And so, there's no questioning I should say, there's very little questioning of experimental results because it actually happened. And so there's really no question whether this is real or not, because it actually happened. Okay. And with the appropriate setup, you can handle very complex and complicated situations. But the downside to experiments is that they're very costly and very time consuming to set up. Okay. You'll see some of the problems that we're going to tackle in this class in our activities, right? It's not exactly practical to build and design an entire freeway freeway sign just to test whether the thing's going to break, right? Usually you want to run a simulation on that or do a calculation. Okay. So what we're going to focus on in this class is what I consider to be the third category of analysis, which is computational analysis. Okay. So computational does have its similarities to the first category. And so in the sense that, we have our governing equations and we are going to solve them for our results. And so there is going to be an element of, does this governing equation even, affect our results? But the difference is that under computational, instead of solving the equations ourselves, we're asking the computer to solve it for us. Okay. And I think, when you first start to get used to computational tools, it's a very different mindset compared to, I think what you're used to in a typical theory-based class. Because if you think back to, let's say, your solid mechanics class or your fluid mechanics class, right? The setup for the problem, every problem that you did was essentially done for you. Right? So the professor or the instructor presents you with the problem and you solve it. Okay. When you're using computational tools, the roles are actually reversed. And so, when you're setting up a simulation to run in ANSYS, you're going to be the ones that set up the problem. You're going to define the geometry. You're going to define the governing equations. You're going to define the boundary conditions, and the computer is going to solve that for you. Okay? And so it kind of shifts the mindset a little bit in terms of, instead of asking yourself, did I solve this question correctly? You're now asking yourself, did I set up this problem properly in order to get a result that makes sense? Okay. And so the nice thing about computational is that, it is still relatively inexpensive. It's still relatively, fast, right? So running a simulation on a computer is always going to be faster than setting up an experiment. But the downside to computational work is that it can be very tricky to set up. And well, maybe that's not true. It's not that tricky to set up, but it is very easy to get results that are worthless. And a lot of times the worthless results are kind of hard to determine. So one of my goals for this class is to help you guys make sure that when you are using a tool like this, to make sure that you get results that are accurate and reliable that you can actually use. That's not just garbage. That's not going to be used. Okay, so let's talk about some examples in terms of the types of problems that you might see in an analytical context, experimental context, and computation. Okay. All right, so what we have here is a very elementary beam analysis, and so this hopefully looks familiar to from your solid mechanics course. And so we have a simply supported beam. So we have a pin support on the left, a roller support on the right. We have a distributed loading, right? And you might be interested in determining, how is this beam going to deform as a result of these conditions, okay? So this is something you can probably solve by hand. There are beam equations that you can solve for this, but, something like this is not terribly useful for, a practical engineering situations where you have, more complex geometry than just a simple beam. You have more complex boundary conditions than just a simple distributed load. Okay. Right. And so in reality, the problem that you may be trying to solve might be something like this, right? And so you're designing this, huge, parking structure, and you're designing the structural beams to make sure that it doesn't collapse on its own weight, or it doesn't collapse when it's full of cars. Okay. And so in these situations, you may have a complex, maybe part where several beams come together, and you want to make sure that the beams are not going to fail under all that weight. Okay. And so this would be a problem that's has a geometry that's way too complicated to compute by hand. And so you can use a simulation like shown here in order to compute your quantities of interest. Okay. All right. And one thing about FEA too is that you're not just limited to structural simulations. Although for this class, we are focusing mostly on structures, just because I would say that's generally the most helpful for mechanical engineers. But you can also run heat transfer simulations. You can run fluid mechanics simulations. We'll touch on that a little bit near the end of the summer session. But FEAs, the rule with FEA is that as long as it's governed by a differential equation, you can simulate it. Okay. Okay. So I know not everyone has taken heat transfer yet, but when you do take heat transfer, this is a very typical problem that you would solve, right? And so you have kind of a rectangular piece of material here. It's subjected to different temperatures on the left and right. And you would be able to solve, what the temperature change is as you go through the material, okay? So for a very simple case like this, a very uniform material, very simple rectangular geometry, very simple boundary conditions, you can solve this by hand, right? So the heat equation is something you can solve for this situation. But once you start to add some complexity, so you can see here we have a turbine blade. It's being subjected to hot gases and in motion, right? And so that's going to heat up the turbine blades as well, right? And so what you're looking at here is a heat map of the temperatures on the turbine blades. And so you can see it's very warm near the near the center. It gets cooler throughout. This is not something you can solve by hand. Well, not practically. So you could solve it by hand if you have an entire weekend to do it, but most people don't want to do that. They want to spend the weekend doing other stuff. Okay, and then one last example here for fluid mechanics. So here is very typical pipe flow. This is something that you can solve for, hand. You can solve the Navier-Stokes equations. But if you want to do something more complex, so this right here is actually a screenshot from my research. This was actually many years ago. But here, this is a surgical procedure that someone is undergoing. And so you can simulate this using finite elements in order to get, some results that might be useful for the doctor to help them plan their surgery. Okay. Okay, so finite elements, is a very powerful tool. There's no denying that. And I think increasingly as computers get more and more powerful, finite elements is something that's going to be a useful skill to have, because that's something that more and more employers are looking to add to their plan. Okay. Any questions on this so far? Okay. Good. Okay, let's skip that just for the sake of time. Okay. So first thing I want to kind of describe here is what I define as the finite element process. So it's a little bit ill timing because I don't think we'll get to use ANSYS today, but we'll go through this first thing tomorrow, right? So every time you do a finite element simulation, you're going to follow this process. Now the details of each of the steps are going to be different depending on the problem that you're doing. But you're going to see that for every ANSYS activity, for all the projects that you're going to do, you're going to go through this process. Okay. Okay. So first step is to define the geometry. And so every finite element simulation, you need to define your domain essentially, right? So you need to define what the part or what the system that you're going to be running the simulation on, right? So for for kind of a more applied class like we're doing, where we're using a software like ANSYS, the geometry is going to be defined by a CAD file. So this will most of the time be a file that you're going to be producing in another software. Usually it's SolidWorks. That's the CAD software that's taught, I would say, almost ubiquitously now in most engineering programs. But sometimes, we'll create the geometry within ANSYS itself. So ANSYS also has some very basic CAD tools. We'll actually use them in Activity 1. But for the most part, we're going to be importing a CAD geometry. That's always going to be your first step, is to define your geometry, because you can't really run a simulation with that. Okay. Next, we need to specify the material properties. And so it's not enough just to define your geometry. You need to specify what your geometry is made out of, because the different types of materials that are out there are going to behave differently when you expose them to forces and loads and boundary conditions. Okay. So whether you have a metal like aluminum, something very common, or steel, versus a composite material versus a polymer like a plastic, right? All of those are going to behave differently. And so you need to specify what material your geometry is made out of. And sometimes you may need to input the material properties by hand. Okay.
Quick question on that, sir.
Yes.
When it comes to the SolidWorks, will we actually use the material editing in there, or would we make the geometry and then do editing within ANSYS?
That's a good question. So there are ways to import the material editing from SolidWorks into ANSYS. Okay. But for this class, I'm going to show you guys how to edit it directly within ANSYS itself, just to be more flexible. Yeah. Yeah, and then with the materials, there's a lot of complexity here as well. And so, there's very simple isotropic properties like metals, or you can have very anisotropic properties. And so, like wood is a very common, building material. That's something that's common. That's something that's actually mostly imported from SolidWorks. And so that's not something ANSYS does particularly well. And so that might be something you might import for the future. But for this class, we'll mostly focus on the simple material properties, but just know that ANSYS does have the ability to do more complex stuff as well. All right, next step. So this is the, I would say the step that I think people most associate with finite elements, which is the meshing, okay? So we're going to spend a lot of time talking about the meshing in this class in terms of, what it is, why it's important, some techniques for good meshing. So the whole idea with the meshing is that, ultimately we want to solve a differential equation on this geometry. And when you have a complicated geometry, that's kind of hard to do, right? So a computer is great, but it's also not a magician, right? So it can't magically solve your governing equation on a very complicated geometry. So we need to help it out a little bit. And so part of that process is to generate what's called a mesh, which means we're going to take our geometry and we're going to break it up into lots and lots of simpler shapes, to make it easier to solve. And and then eventually we're going to make the connection in terms of how do we take this simple shape and how does that lead to a system of differential equations or a system of linear equations that the computer's going to solve. All in good time. Okay. So the idea with the mesh is to choose a simple shape, right? And so in 2D we have you can either break it up into triangles or rectangles. In 3 dimensions you can either pick a tetrahedron or a hexahedron, right? And then what the software is going to do is that it's going to break up your geometry into all these tiny shapes, which we call elements, right? Hence the name finite element analysis, right? And I always tell people, think of if you were to take your geometry and if you were to construct it with a bunch of identical Legos, that's essentially what you're doing. And there's a lot of room for variation here in terms of the size of the elements, the shape of the elements. We'll go over a concept called the order of the elements in terms of what that means and how that affects your results. So matching, very important part of FEA, and honestly the time that you'll probably spend the most you'll have the most frustration with, especially with your final project. Meshing can be very tricky for certain types of geometries, and so. But it is a very defining part of the finite element analysis. All right. Next, we have to apply boundary conditions. So boundary conditions, basically, what I always tell people is that boundary conditions define any kind of external effects or any kind of external forces that are going to be affecting your geometry. Okay, because even with a powerful computational tool, right, it's going to be impossible for us to simulate an entire engineering system. Right. Most of the times you're only going to be simulating just a small portion. Okay. So, just take an example, right? So, I always get, a lot of the people from Formula SAE here, and they want to throw their entire car into ANSYS. And I said, maybe that's a little bit too difficult to do. Maybe let's look at a few components together, right? But when you do that, you have to define how those components connect to other components that are not being, simulated at the same time. And that's what the boundary conditions represent. So any kinds of fixed constraints, any kind of places where your geometry is going to have no deformation, any kind of external forces, external pressures, distributed forces, those are going to be in the boundary conditions. Okay. So we are going to talk about boundary conditions a lot in this class. Probably, meshing is probably we're going to talk about the most. Boundary conditions probably the second most. And so how you define your boundary conditions, obviously has a big impact on your result. And you want to make sure you do that correctly. Okay, next step is a step called assembly. So, if you're just using the software as a user, this is a part that ANSYS essentially hides from you. But it's important to kind of know what's going on. And so what's happening underneath the hood in ANSYS is that basically ANSYS is generating this matrix set of equations to solve and then solving that system. Okay, so I would say maybe about halfway through the class, we're really going to get into the theory behind finite elements. And you'll see how a system like this is generated from a finite element problem. Okay, and the last step is to solve, right? And so this is also a step that the computer typically does. And so, usually after the assembly step, you're going to have a massive system of algebraic equations, usually on the order of, it's not uncommon to have 1 million equations and 1 million unknowns. And so that's obviously not practical for humans to solve. But the computer can solve that very well. So this is the part where the computer does it. And this is the part where you kind of hit solve and you kind of wait for the computer. Sometimes you're waiting for a couple minutes, but this is essentially what it's doing underneath. All right. And then the step that I think, a lot of people like is the post-processing. So once ANSYS or once your software is done solving for the solution, then it's time to display the results. And so this is probably what you've seen before. If you've heard of ANSYS before and you've heard of FEA, you've seen these kind of color contour plots where you can see, things like the deformation, things like the stress. You can even compute things like factor of safety. So that's what this simulation shows here, right? And it's all color coded. And so based on the colors that you see, that's kind of the simulated result, okay? So from this result here, you can see that, everything in red here has a factor of safety of 7. So those are areas that are very safe. So those are areas that are very unlikely to fail for this part. But for the parts of the geometry that are, either lighter blue or dark blue, those have very low factors of safety. So those are at much greater risk of failing. Okay. And that's something that you can do with FEA is that, not only can you predict whether or not your part is going to fail or not, you can also make predictions in terms of where it's most likely to fail. And that is, very valuable information as you're designing your engineering systems. Okay, so that's the finite element process. And so that's something we're going to follow for every ANSYS activity, every project we're going to do together. Any questions on any steps in this process here? Okay, good. Okay, so like I mentioned, we are going to spend some bit of time on the background knowledge, and I get this question every time I teach this class, and so I know everyone's kind of itching to use ANSYS, but we do have to learn background knowledge, right? So I always like to tell people that you're taking this is a university course in finite elements. It is different than if you were to take like a certification course in ANSYS. So those do exist. And if you're just interested in kind of just learning to use the software, that's something that is an option. But this, the way that we kind of package it here, the way that we kind of have to teach it, there has to be some kind of theoretical knowledge, okay? And there's a reason for it, right? And it's not just because I think it's cool, although I do think it is really cool. But, finite element simulations, as powerful as they are, as useful as they are, at the end of the day, they are just a tool for you to use. Okay, they're not going to be able to. They're not just a miracle pill that's going to do all of your engineering work for you. Okay, in that sense, it's no better than SolidWorks, and you can make the argument it's no better than a hammer or a saw, right? And so while it can be very useful, it does have limitations and it does have best practices that you have to know how to use so that you don't misuse it. Okay, because the way that we position this class, this is a senior level elective class. For a lot of you, this is going to be your only exposure to FEA, right? And so for a lot of you, you're going to take this class, and then after you graduate, you're going to, you might be put in a position where you have to use this professionally, right? And as a professional user of finite element, professional user of ANSYS, you have not only do you have to know how to use it, you have to also be aware of its limitations and where it's best used. Okay, because it's not going to work all the time. Right? And just like any tool, right? You're not going to use a hammer for a job that's suited for a bandsaw, right? And so, same thing with finite elements. And so understanding the theory, understanding the fundamentals and the concepts behind FEA will help you kind of debug problems when it doesn't work as expected. It'll help you kind of not put it in positions where it's going to give you a wrong result, right? That's the reason why we learn the background knowledge. That's the reason why we learn, right? And, like I mentioned, as an expert in FEA, or that's my goal at the end of this class is for everyone to be an expert. It's your responsibility to know these things so that you don't misuse it or report incorrect results. Okay, because while in this class, it's okay to get wrong results. It's okay to get things wrong, right? Once you're out there working in the real world, right, and you're using this to design a bridge, you can't really afford to get that problem wrong, right? You really need to get that right. So you really need to kind of learn that theory now and make the mistakes now so that you don't make it. Okay. All right, so let me give you an example from another professional that I think people have a better understanding, right? So if you think about your veterinarian, right? Your veterinarian is someone that will be tasked to take care of our pets. And so on the one hand, we expect them to know procedural skills, right? And so we expect them to know how to give a shot to an animal, how to take blood pressure, maybe performing tests on their eyes and ears, okay? But we also expect them to know conceptual information and background information in terms of what they're doing, right? We also expect them to know why and when to give animal shots, right? So we don't want them to just randomly give our cat a shot just because they feel like it, right? We also expect them to basically interpret our pet's signs to know when they're sick, okay? And so it's the same thing for us, right? And so, anytime you have a professional, there's always an expectation that they have kind of an understanding of why they're doing what they're doing. Okay, and that's the reason why you take a course. Okay, and I think the last thing before the syllabus, we have a couple more things, is why ANSYS, right? So we are going to focus on ANSYS in this class, but like I mentioned, ANSYS is not the only finite element software that's out there. There's a lot more, I would say, specialized softwares for more specialized problems. There's also a lot of generalist softwares out there as well. So another one that's very parallel to ANSYS is called Abacus. And so why do we use ANSYS in this class? So ANSYS, for one, is there's a free student version, so that is a big motivator. I'm not going to lie. And so, one thing I'll show you guys today is how to download the free student version of ANSYS to all of your personal computers. And so that's available for everyone. So, while we will have this class in the lab room and ANSYS will be available, granted that the license server is working, I think a lot of people in this class find it more convenient to work on problems at home, which is perfectly fine. And so, the fact that ANSYS has a free version that's very easy to just download and install just from their website, that's a big factor. But it's actually very genius because ANSYS has done this for a while. And as a result, a lot of university programs and a lot of credential programs have used ANSYS just because it is so accessible. And so we have this kind of almost generation of students, engineers that are coming through where the only finite element software they know is ANSYS. And so it kind of forces these companies to buy ANSYS for their companies just because that's what their employees are trained on. And so because of that, it is one of the most widely used finite element softwares that's used in industry. And so it is a useful skill that, certain employers for certain positions look for, right? And so that's something that I definitely take in mind. But also, a lot of the skills and a lot of the concepts we're going to learn in this class are not just unique to ANSYS. And so, I feel the same way towards programming languages as well. And so kind of once you learn one software, once you learn one programming language, those same concepts in terms of how you set up an FEA problem, how you do the mesh, how you do your boundary conditions, those skills will also translate to another software. The only difference is that the buttons are going to be in a different location, which, usually doesn't take too long to learn. Right. So we're going to focus on just one, just so that, we can really nail down the concepts and understanding. But, a lot of the skills you're going to learn in this class are also transferable to other softwares as well. Okay, and the last thing, before we go into the syllabus is to ask ourselves, why do we need to learn to verify and interpret the results? Okay, so like I mentioned before, FEA is just a tool, right? It's going to give you results, but they're not always going to be correct. And so an important skill for you guys to learn from this class is to be able to basically analyze and determine, from an FEA result, based on how it's set up, based on its mesh, based on its boundary condition, whether that result is going to be reliable. Okay. So there's a saying that we have, not only in FEA, but for all of computational engineering, it's called garbage in, garbage out. And so if you put garbage into your software, right, the software is not going to magically fix it and give you the result that you're looking for. You're going to get garbage out, right? And so if your mesh is not good, is not well refined, if your boundary conditions are incorrect, if your governing equations are incorrect, then of course you're going to get the wrong result, okay? And so, one important skill is to that I want you guys to learn from this class is to check all those things and just make sure that what you're getting is good. Okay. Okay. Any questions on any of that before we jump into the syllabus? Okay, good. Okay, so the next, I would say maybe like 30 minutes or so, we'll talk about the syllabus and then we'll talk about the course website. I'll check with IT to see if we can get answers for today. But if not, I do have a lecture that's prepared. Okay. And by the way, so these classes are very long. So these are 3-hour classes. I can't keep going for 3 hours. That's a little bit too long for me. So we'll usually take a break in the middle. And so after we finish with the syllabus, after we finish with the tour of the course website, we'll probably take a 10-15 minute break, and then we'll come back and we'll finish the lecture. Okay, so the syllabus is available to you guys on the Canvas website. And so I think some of you have already taken a look. So I think I did email everyone in the class with it. But you can still download the PDF on there. But these are going to be the important points. Okay. Okay, so first, office hours. And so you don't need to make an appointment for office hours. My door is open during all these times. And so if you ever have a question about the class or even just a question in general, summer's pretty lonely. So I just finished teaching a summer session and not too many people came to office hours. So I'm just kind of sitting in my office, just waiting for someone to say hi. So, if you're on campus, don't be afraid to come by. So my office is in engineering. So it's in not this building, it's the building that's across the quad. It's on the second floor. And so basically if you go up the elevator, you go up the stairs, you turn right, you're going to reach a hallway at the end, you turn right again. I'm right at the corner. Okay. And office hour times are very easy to remember. It's basically 1:30 to 2:30 every day before the lecture. Okay. And you can attend in person or on Zoom as well. Right. And so I do have Zoom links for the office hours. If you've seen the course website, you've probably noticed them. And so, I do have the Zoom room open. And so if Zoom is more convenient for you before the lecture, that's perfectly fine as well. So office hours, these are great times, if you ever have questions on what we are discussing in the class, you have some things that are confusing, feel free to drop by, ask questions about those. If you have questions on the homework or questions on the projects, I basically answer almost anything in the office hours. And so, feel free to come by for okay. Okay. Course learning objectives. And so, like I mentioned earlier that, I do have learning objectives that I post per day, but, I do have learning objectives that I use to organize the entire course. Right? And so my hope is that by the end of the summer session, by the time we reach the conclusion of this course, you'll be able to do all 4 things on this list here. Okay. And some of these might make sense after today, but I think some of these also, will take some time to really, some of these use terms and use concepts that we haven't introduced yet. And so, we'll return to this, later on in the summer session. But just know that, I'm not just up here just doing random stuff. There is an organization, there is a logic, and part of that is these course level. Okay. Oh, I'm sorry. One point on not related to office hours, but but related to Zoom. So you might have noticed if you look on the course website, there is a Zoom link for the lectures as well. In fact, a couple of people are on Zoom right now. So I don't mind if you attend the lectures on Zoom or you come in person. Now it is a little bit easier if you come in person on the days that we do ANSYS, just because, if you are running into issues or you're running into questions with the software, it's a lot easier for me to kind of go around and kind of help you out that way. We can do share screen on Zoom. That is possible, but it's just a little bit more clunky. But whether you attend in person or on Zoom, it's no issue. Just because I know, with just how traffic is in Southern California, and it's not always easy to get out here, especially at this time of day. After we leave, I know rush hour traffic is crazy. So, if it works better for you to attend on Zoom, that's perfectly fine with me. There's only one day this summer session where I am going to require everyone to be in class, which is the day that we take the exam. And so I believe that's going to be the Tuesday of the last week that we have in this class, or Tuesday of week 5. That's the only day that I require everyone to be here, just because you have to be here to take the exam. Every other day you can attend on Zoom, but I would recommend you come in for the ANSYS activity days, just so it's easier for me to kind of get around. It's not a requirement. Okay, let's talk deliverables. And so for this class, there will be 7 homework assignments. And so 6 of those will be ANSYS activities. And so those will be activities that will start in the class, but there will be portions that you'll have to do by yourself as well. And there's going to be 1 problem set. And the problem set is going to be based on the theory that we're going to learn. Okay. There's going to be 1 midterm exam. I call it a midterm exam, although it's kind of like a pseudo final because it's going to be at the end. There's 1 midterm project that's going to be due at the end of, I think, week 3. And 1 final project which is going to be due, basically the weekend after that last week. Okay, so that's everything that you need to do to turn in for this class. Okay, the lowest homework assignment will be dropped, right? And so, that it is a lot of assignments, especially for such a short summer session. And so, I do want to give you guys a little bit of flexibility. But just know that all of the activities and all of the homework assignments, or the 1 homework assignment, are really designed to be helpful to you, right? And so they're either going to be teaching you a new feature or a new tool within ANSYS, or they give you essential practice for the midterm exam. Okay. The midterm exam will not be cumulative, and so what I mean by that is that if the midterm exam is not going to be based on ANSYS at all, it's really just going to be about the theory of finite elements that we're going to be learning later on, right? But I'll make that clear once we get closer. So I'll publish a study guide for the midterm exam as well. Okay. And so these are all the dates that I've planned for everything this session. So the midterm project is planned to be due on Sunday, July 19th. Midterm exam or midterm project is Sunday, July 19th. Midterm exam is going to be Tuesday, July 28th. And then the final report for the final project is going to be due on Sunday, August 2nd. So that's the Sunday after the summer session. Okay. All right. Any questions on the deliverables for the class? Okay, course grades. And so this is how the grade breakdown is going to be. I may adjust this a little bit. The midterm exam, I think I may have made it a little bit too high. So I may take 5-10% off that and put it in other categories. But this is kind of what I'm thinking right now. So for the most part, just because for most of this class, the homework assignments are all ANSYS activities. I am probably going to count them 5 to 10%, although I may increase that to 10%. Homeworks are all going to be graded on completion, and so unless you want me to, I'll mostly just check it for completion. If you want me to leave feedback, I can do that as well. Midterm project is going to be worth 15%. Final project will be worth 30%, but I may shift some things around. So I may make the midterm exam worth 40% and then move 5% into the midterm project and the homework. Okay. And so based on that, based on your final scores, I'm going to assign letter grades based on the following scale. So I think this is pretty standard. So 90% and above is going to be A, 80% and above is going to be a B, 70% above in the C, right? And then, D's and F's as well. Okay. Now at the end of the course, so I don't do curving in the traditional sense. And so what I mean by that is that, sometimes when I took college courses, the professor kind of decided beforehand that only the top 10% are going to get A's. So I don't do that. But what I do at the end is that if the class average is lower than kind of what I usually like to have for these types of classes, then what I'll do is I'll add points to everyone's grade until the average is up there. Okay. So for an elective class like this, I'll just be very straightforward with you. For an elective class like this, I like the class average to be kind of low 80s, maybe 80, 81%, just because, you guys are choosing to be here. You didn't have to take this class as an elective. And so if I do see at the end of the class that the class average is maybe 75, 76, 77, I'll add, 4 or 5 points to everyone's grade until we reach that. Okay. But I will say for this class, usually I don't have to add points just because the project grades tend to be higher, just because, you guys, students typically do a pretty good job in this class. But, if there is kind of a short or, we're not at that threshold at the end, I will add points to everyone's grade. I do that evenly for everyone. So I don't, I don't add points selectively, just everyone gets a boost. Okay. Okay, any questions on the grading policy? Okay. All right, textbook. So there is no required textbook for the class, just because, I still remember, it's been a while since I've been a student, but I still remember being very resentful about how expensive textbooks were. So there's nothing required for this course. In fact, a lot of what we're going to do in this class is kind of ANSYS activities that I've kind of developed in kind of concert with some other workshops that I've attended in the past. So those are all going to be provided for you. But if you did want to pick up a textbook for this class, these are the two that I'm mostly referencing. And so the first textbook, the Logan textbook, that's going to be the textbook we're using for the theory portion. And so that's called the first course in finite elements. I'm using a 4th edition just because that's just the one that I have. But I think there's probably other versions of the textbook that have come out as well. And then for a lot of the ANSYS stuff, a very good reference is this series by STC Publications called Finite Element Simulations with ANSYS Workbench. So I'm using the 2020 version just because that's just the one that I have. But they've come out with other versions as well. Okay. So both of those are good references. The second one, especially if you do plan to use more ANSYS as in the professional life, but you're not going to be required to get this up. So the full problem statement of everything that we do is going to be published, as well as all my lecture notes. So all of my lecture notes will be available to you guys as well. And so, I basically just teach straight from my lecture notes. And so, you don't need to pick up the textbook to do any additional readings. But, if you do want to pick one up, these are what I recommend. And I always recommend, don't pay full price for a textbook. Try to find a cheap version, maybe something that's used, or maybe just happen to be sailing the high seas on the internet and you find a PDF. That's always a good option as well. All right, course website. So, I think by this point, I think probably everyone is accustomed to Canvas. I think a lot of you have kind of been here for a while. But just the way that I use Canvas, and so basically anything that I create for this class, any kind of content, lecture notes, tutorials, ANSYS activities, lecture slides, will be available on Canvas, right? All of my lectures are being recorded as well. So, I am streaming this on Zoom, and I'm having Zoom record this automatically. So basically at the end of the lecture, although usually the next day, just because the lecture is so long, it takes a while to process, I'll upload the recording for the lecture onto YouTube. And then I'll put the link for that recording onto the Canvas site. Okay. And so if you want to kind of look at the ANSYS activities, you want to see how I kind of do certain things, then those will be available as well. Okay. Any kind of announcement will be made through Canvas as well. And so I think Canvas emails that to you automatically. And so if you're not getting the announcement emails from Canvas, just definitely let me know, and then we can kind of solve that issue. Okay. And you'll see once we kind of tour the course website that I do update the Canvas site. And so at the very least, each day I'll be updating it with the lecture recording, and I'll be updating it with kind of the topics and the learning objectives for the day as well. So please make sure you're checking the Canvas site regularly. Okay, course policies. And so so for homework assignments, even though this class is graded based on completion, I do accept late homeworks. And so my policy is that each day that the homework assignment is late, I do dock 10% off its points. But you can turn in an assignment up until the availability date on Canvas. And so you'll see on Canvas, we'll kind of take a tour in a moment, that every assignment has a due date and has an availability date. And so you can turn in the assignment up until the availability date. And then after that, I won't accept it, right? And then each day that it's late will be docked 10%. Okay. Regrades, and so this will only for this class only really apply for the projects and the exam. But I do accept regrade requests, right? And so if you feel like you were graded too harshly or unfairly, definitely let me know. I'm definitely not a perfect person. I do make mistakes when I'm grading as well. Especially for the projects. And so for the midterm project, I'm going to try my best to leave as much feedback as I can. But, if you feel like, for a certain category, you've lost kind of too many points, definitely let me know and we can discuss a bit more. My only requirement for regrades is that you request it within a week after I grade something. So, for this class, it's going to be a bit hard just because the summer session is so fast. But for say like the midterm project, I'll grade it and I'll upload your rubric. You'll have a week from that point to request a regrade. Okay, and then emails. And so emails is my preferred method of communication. And so I know Canvas has its own messaging system, but I do prefer that everyone just email me directly, just so that all my messages are in the same place. With that said, please use the kind of this EGME 410 in square brackets in the subject line, just so that I know it's from this class. With such a small class, I think eventually I'll probably get to know everyone's names, but it does help me out to have that EGME 410. Okay. I'm usually pretty quick with emails, and so I'll usually respond to you same day if I happen to be at the computer. Worst case, I'll probably respond to you the next morning once I get back to my computer. Right? And then I think a few of you have already sent me your introductory emails, and I think I've already responded to them as well. So my policy is that I will definitely get back to you within 48 hours, except for weekends, of course. Weekends are for my family and my son. But within the next 48 working hour days, I will get back to you. Okay? Okay, graduate credit. I think we may have a couple grad students in this class, and so if you are taking this for grad credit, definitely let me know. I do need to have you do an extra assignment just because that's the policy that we have. If you're an undergraduate student and you're taking this for grad credit, I know some of you may be taking this with the blended program. Definitely let me know as well. There is a form that we have to fill out. Just send it as part of your introductory email, and we'll get that sorted. Okay. Last thing, before we tour the campus website, which is academic dishonesty. So I will say for a class like this, there's a little bit less of an issue with this just because, again, all of you chose to be here. So all of you have at least some latent interest in learning ANSYS. And so, it's not one of those things where, you're paying someone else to do it for you or using AI to do it for you. But, we do have very strict academic dishonesty policies within the department. And so, any act of academic dishonesty, whether it be plagiarizing or using an AI tool to do your assignments for you, is will not be tolerated. And so, the policy that we have in the department is that any act of academic dishonesty will result in at least a 0 for that assignment, up to an F in that in the entire course. Along with that, a referral to student conduct. Okay, so please don't do it. What I always tell people is that, you're taking this class for a reason. And that reason is not just to get the letter grade at the end, right? My hope is that, at least if I do a good job, if I do my job well, that, you're going to walk away from this class with skills and knowledge that you can apply towards your job or towards your professional life or just or anything, right? And at the end of the day, if you're cheating or if you're using AI or you're plagiarizing, you're not obtaining those skills, you're just turning in an assignment. And that's essentially not going to be useful to you. It doesn't build skill, right? So my promise to you is that, I will do everything I can to help you when you're learning, to help you obtain these skills, if you give me a chance, right? And so if you ever feel like you're falling behind, if you feel like the course is going too fast, you're not kind of keeping up, ANSYS is just very confusing for you, just let me know, right? So just send me an email. I'm always happy to, make an appointment to see you. I know that office hour times can be a bit difficult because it's before the class, and so if you prefer to meet outside of that, definitely let me know. I'm always open to that. Anything I can do to help, just let me know. Okay. But if you resort to academic dishonesty at that point, there's not much that I can do, and we just because we have kind of a protocol and a procedure for that. Okay. But please use me as a resource, right? And so I'm not just here to grade you. I do really believe that I'm here to help you, learn these skills, right? And so that's what I consider my primary responsibility to be, which is to teach skills and not necessarily just to gatekeep. Okay. I know, not everyone has that experience in their university classrooms, but that's how I view my job here is to teach skills, not necessarily just to gatekeep and assign grades. Okay. All right. So last thing before, I think I've probably said it 3 times. I'm sorry, but the first homework assignment. So homework 0. So homework 0 is the email introductions. So your very first assignment for this class is just send me an email just to introduce yourself. And so I know the summer session is going to be very short. It's just going to be the 5 weeks, but I still want to get to know everyone. And so please send me an email with your name at the very least and your class standing. Okay. You'll get full credit by just doing that, right? I've had some students just send me literally just a blank email, and I give them credit because that's what the assignment is. But the more you write, the more pleasant it is generally. So I have these 4 questions here. You don't necessarily have to answer these questions, but if you're having trouble kind of thinking about what to write, then you can answer questions of what kind of career would you like to have after graduating? What are some of your hobbies and interests? Any concerns that you have for the class? Okay. So anything that you feel like writing about, then please write. Okay. And I do read every single one, right? So I don't just delete them. I do read every single one. I do respond to every single one. So please write this, and it's kind of a ritual that I've started kind of when I first started working here. And it's my favorite part of the class. So please send me an email. Please do it by this Sunday. So the due date for that is this Sunday, July 5th. And we'll get full credit. Everyone starts the class with me. All right, any questions on this before we tour the Canvas website? Okay. All right, so that is the introductory slide. So let's go ahead and jump to the Canvas site. Okay. In fact, let me go ahead and switch to student view so that I see what you miss. Okay. So when you come to the course website, this is basically what you see. So this is the home page. So you can see here we have the name of the course. That's me. These are the class times: Tuesday, Wednesday, Thursdays from 3 to essentially 6 p.m. 5:50, and they're taking place in CS304, which is this room here. Okay. So this blurb here is lifted straight from the syllabus. So this is just a description of the course. Here are the course level learning objectives, and this is the syllabus. And so if you forget kind of anything that we kind of talked about just now, everything that I talked about is on the syllabus. Okay. Next, we have the Zoom links. And so if you prefer to attend the lectures on Zoom, this is the link that you will have to follow here. You do have to sign into Zoom. I had an issue over COVID where, I had just randos just bomb my lecture session. So you do have to be a registered user of Zoom. I think you have to have a Cal State Fullerton account as well. So, that's available there. And these are the links to the office hours. They all lead to the same link. I only have just one room for the office hours, but, I have this here just to remind you of the times. Okay. All right, and so at the bottom of the course homepage, you're going to see here, this is our course outline. So this is day by day, every single topic, every single type of thing that we're going to do. So this is kind of the planned schedule for the whole summer session. Okay, and you can see I've broken up each week into 3 different parts. So we're at week 1, part 1. Tomorrow's going to be week 1, part 2. Week 1, part 3. Okay. And eventually, all of these pages here will become clickable, right? And so right now, the only one that's clickable is just week 1, part 1, just because that's today, okay? And so if you go to that page, you can see here, this is the page for today, okay? So for every day, every lecture that we have, I'm going to make a page like this that basically just has a brief description in terms of what you're going to expect to learn. These are the learning objectives for the day. Once I post the lecture recordings, it will be here as well. Right. And so if you're wondering kind of where to find the lecture recording, let's say you want to kind of view a certain part of the lecture from today, you just go to that weekly page, and this will eventually become clickable once I've uploaded the lecture. Okay. Any assignments due that week or due soon will be here as well. And any files, any kind of PDFs, lecture notes, and homework solutions will be posted here as well. Okay. All right, so this is something that I do recommend that you check each day. At the very least, check them before the lecture. At least download the lecture notes for that day, just so that you're kind of on top of that stuff. Okay. Okay, so that is the home page and the weekly page, and so this will be updated basically every single day here. Okay. Next, we have the announcements tab, and so for the most part, I think this tab is not that helpful because you get emailed all of these, but if you did want to see a record of all the announcements that I made, those are here as well. Next, we have the assignments tab, and so this is basically all the assignments that are going to be out there. Okay, so you can see the introduction assignments here. Answers activity 1 is posted as well. I think I'm gonna adjust this due date because I think we're gonna do the first answers activity tomorrow. Yeah, looks like the license server is not gonna be up. So we'll do the first answers activity tomorrow, if not Thursday. So I'll adjust the schedule as well, but that'll be here as well. Okay. Here is the grades tab, and so this is where you can view your current grade. Okay. Here is the grade breakdown. So again, I think I'm going to adjust this just to make it so the midterm exam is at 50%. That seems a bit high in sight. Okay. So this will have all the scores for all of your assignments here. But I think if you've used Canvas before, you should be used to this. Okay. Next is the People's tab, and so this is everyone that is in the class. This class is going to be all individual work, so there's going to be no group work. So probably this tab's not that useful, but this is enabled by default on Canvas, so I just kept it there. All right, and then the last tab here is the Files tab, and so this is also a section that you're probably not going to see because any file that's relevant for a given day, I'm going to post here on the weekly pages. But if you're looking for a very specific file, so let's say you're looking for the project specifications or the project rubric, right? You may be able to find it a bit more directly from this here. Okay, so any kind of PDF, any kind of lecture notes that I post for the class will be available here, right? And you can kind of search for it directly. And the last tab here is the SOQ, which I don't think is not available yet, which makes sense because it's the first day, right? And so you don't leave a Yelp review on a restaurant after you eat the appetizer, right? You have to eat the whole meal, and so I think this will be available at the end of some session. Okay. All right. Any questions on the Canvas website? Okay. All right. So that's it for the introduction. So I do have some lecture notes that will start after this, but let's take a break. We did finish a little bit earlier than I thought, so let's come back at 4:15, and then we'll start the lecture from there. Okay, if you have any questions that you want to talk to me individually, I'll just be up here, so you can just come up and chat. really awful. So I'll join the Zoom call on the coding computer here as well as my iPad, and then I'll write there and kind of talk and write. That way, I kind of give myself some breaks with talking. And so, in some ways, maybe it's good that, we're doing our ANSYS activity not today. But I think, there are some important concepts for us to go over just to kind of give our ANSYS a bit more context. Okay. So today's kind of be a little bit of a double header. So I have one set of lecture notes, which I call theory behind FEA. So this is kind of just the just very brief introduction, a little bit kind of a follow-up to kind of what we just discussed in the introductory slides. And so we'll introduce the idea of a boundary value problem. We'll introduce the idea of a linear system. We'll talk about kind of the different components and kind of what goes into it. And so I said that's kind of something good to know before we start ANSYS. And then we'll also do a very quick review of solid mechanics as well. Okay. And I will say I'm not a solid mechanics person. I'm by trade, I'm very much a fluid mechanics person. But there is a bare minimum amount of solid mechanics that you should know before as we use ANSYS. And so concepts like stress and strain and material properties and kind of what those represent. We'll review that just to kind of give our simulation results a bit more context when we do it either tomorrow or Thursday, depending on the classes. So, okay, so let's go ahead and get started. Okay, so first we're going to talk about theory behind FEA. Okay. So, like I mentioned, earlier today that, for the most part, this class is going to be application focused, right? So ANSYS is going to be a big part in terms of what we're doing here on a daily basis. But, we still need to understand a bit about theory, a bit of what's happening underneath the hood. Because if you don't, then, whatever software, whatever tool that you end up using is just kind of a black box, which, you never, on the one hand, it's not necessary to understand all the intricacies in the coding and the structure behind every software, but you should understand a bit of what's going on, just so that it's just not completely foreign to you. Okay. So just to kind of remind you, finite elements. Finite element analysis is basically a numerical technique, or not even numerical technique, is a technique for solving partial differential equations. So when you take it kind of at its pure kind of state, right, in terms of what FEA is, it really has nothing to do with computers. It has nothing to do with ANSYS, and it really doesn't have anything to do with engineering at all, right? So and I will say I'm not usually one to talk about the history of certain things, but I think FEA is actually very fascinating because when FEA was first, I would say, developed, or when it was first kind of conceived as kind of a technique, it was very largely ignored because this was kind of before the era of computers was kind of really big. So when people kind of first thought of FEA, people really didn't find it useful at all because you took a problem that was already very difficult to solve in a differential equation and you transformed it into another problem that was very difficult to solve. It's just in a different form. Okay. So the idea with FEA is to take, a system, right? So usually, for most physical systems, there is some partial differential equation that governs its behavior, right? So we have something like this. So you have some partial differential equation. So what I'm writing here, this is the heat equation. And so if you've taken 407 before, this probably looks a bit familiar. Right, so the details of this equation are not that important, but this is just to illustrate for a given engineering system, there's some differential equation that governs its behavior that's more or less kind of impossible to solve on a practical standpoint. Okay? Right, so every physical system has something like this, right? So for fluid mechanics, we have the Navier-Stokes equations. For solid mechanics, we have kind of the equations of elasticity, right? So there's always going to be some underlying equation, and if it's in it, even if it's not obvious, there's probably some fundamental conservation of energy, conservation of momentum, conservation of mass equation that you can use to form an equation like this. Okay. And so the idea with FEA is that we can apply FEA as a technique to transform this, right? So the idea is to take a problem that's governed by this differential equation, but instead of solving that differential equation, we solve a different mathematical problem. Okay? And the different mathematical problem is an algebraic one instead. So by utilizing FEA, we transform this into a matrix set of equations. And so I've just kind of just drawn generic matrices here, but what we've essentially done is we've transformed this into a matrix set of equations, right? So kind of our traditional kind of X equations and X unknowns, right? So we have here, this is a square matrix of coefficients. That's going to be multiplied by a vector of unknowns, right? So the unknowns are typically what you're solving for. So those are things like temperature, deformation, stress, things like that. And on the right-hand side, that's where we have external effects like, forces and boundary conditions, right? So when FEA was first introduced, right, you can kind of see why people would kind of brush this off, right? And so on the one hand, we have differential equations, very difficult to solve, right? But then you do all this effort through FEA, and FEA is not a very trivial process. There's quite a lot of work. So we do all this work with finite elements, and what we get out of this is a very large system of algebraic equations, right? Where this matrix, like I mentioned, it's not uncommon for this matrix to have millions and millions of rows or columns. So we have a mathematical problem that's impossible for humans to solve. We go through all this effort through FEA, and we get a mathematical problem that's impossible for humans to solve. So you can kind of see why people were not too impressed with FEA to begin with. Okay, but as computing and as computers and stuff developed, what we found out was that computers are very good at certain tasks, and one thing that computers are actually very good at is algebra. And so that's kind of when FEA really started to take off. And so, as we started to find out that the way that computer processors are kind of developed and kind of designed, that these linear algebra problems are very efficient to solve. And so that kind of revelation spawned a whole set of different computational techniques and tools, right? And we're still kind of making use of it today. So a lot of kind of what we understand about artificial intelligence, kind of the dominant kind of methods for training these networks, are based on linear algebra, right? So if you can take a problem, basically kind of the gold rush of computational engineering is that if you can take your problem, if you can formulate it in terms of an algebraic system of equations, right? Then you have a computational technique on your hands, and maybe something that's going to redefine an entire era of technology. Okay, but FEA was obviously developed a lot faster than AI, and this was kind of the main kind of method that kind of sparked that. Okay. And so kind of once that connection was kind of formed, people started to kind of connect the dots with everything, right? And so people started to realize from at least from an engineering perspective that most engineering systems are governed by physical laws, right? So conservation of mass, conservation of momentum, conservation of energy, and those have corresponding partial differential equations. Right? So whether you're designing a building, whether you're designing a heat pump, right? So there are governing equations that govern this behavior. Okay? We can use FEA to basically formulate those governing equations for a specific system into a set of algebraic equations. Right? And then once we obtain that algebraic system, we can use computers to solve it for us, okay? Because oftentimes these systems are way too large for people to solve. And then once we have that solution from the computer, we can then use that to inform our engineering work, right? So whether we're doing design work, whether we're doing analysis work, right? This really started to become a tool that we can use for for any kind of engineering work. Okay. So that's kind of the thought process, right, of using FEA. And eventually from this, a lot of different softwares started to form. Just because, even though it is possible to write your own FEA code, if you eventually come back for grad school, we do have a course on that. So that's 541. In fact, I just taught that this past spring. And so if you were interested in learning how to do that, there are methods. But, I would say for the most part, most engineers and just most kind of people that use FEA kind of use it as a user, not necessarily from a developer's perspective, right? So for the most part, things like this, at these sections here, right? So that's kind of the nitty-gritty of FEA in terms of, forming this algebraic system, writing the computer code to solve it. For the most part, most people are not that interested in learning about these things. And so these are the parts that are automated by the software. Okay. So if you're using a software or using Abacus or something, then these are the parts that are formulated. So for the most part, these are mostly invisible. You might see this in the sense that maybe your simulation is taking a few minutes to run, and so this is kind of what it's doing. But the idea is that these engineering softwares like ANSYS are designed to you input your geometry, you input all the boundary conditions, and you get a result from it. Okay, so you really kind of only see the first step and the last step. But this is kind of everything that's kind of happening under the hood, at least from a high level perspective. Okay. Okay. And so we will be diving into, that middle block, they're probably kind of halfway through the class. But for the first part, there is a lot of kind of prerequisite knowledge that we have to learn in order to just use ANSYS properly as a proper proof. But that's kind of a little bit of information on the history of the development of FEA and how we kind of get to the point where we are using it now. It's kind of like a modern tool. Okay. Okay. Any questions on this so far? Yes.
So you kind of mentioned in the beginning, like computers, people realize that computers could kind of work well with the wall and road and stuff without. That's when the FEA kind of took off. Then you also kind of mentioned a little bit of AI and stuff like that. The way that AI would kind of tackle something like this, would it just be through, just similar models of a similar part?
So AI kind of works fundamentally differently. So with FEA, we're solving for solutions to these governing equations, and so you have to kind of decide beforehand that you're going to solve these. AI kind of looks at things just purely as input output. And so it sees a connection with this combination of inputs and it says this is what the output should typically look like, but it's not solving any kind of fundamental equation on the inside. And so, I would say, for AI, people kind of describe that usually as like a data-driven approach. And so you need a lot of data to inform that type of model. But for FEA, all you need is just a governing equation. And so for situations that are a lot more novel, that necessarily don't have a lot of data for, I'm going to trust a physics-based model like FEA a lot more, just because there's just not a lot of data in those situations. Yeah.
So, like, what are some things that like AI would play with, and like there's enough data for? Which is just like simple parts, like it's a L bracket, or it's pretty simple, or like more complex stuff is just like
So
you just feed it like old stuff. I'm assuming.
Yeah, so typically the more complexity, the more novel it is, then AI is going to struggle with that because it's going to be looking at just certain features and trying to associate that with the particular output. You're not going to get as detailed color contours like you're going to get in FEA as well. And so, for the most part, you're going to be working at companies that are doing fairly novel stuff, right? And so companies are not usually going to be sharing details of their designs with others. And so there's nothing to really train the AI on in those situations. And so, if you're working on something that's more open source, that there is a lot of data on, then, AI can probably give you a somewhat reliable result in that case. But FEA is there's a reason why this is the tool that's trusted more for engineering work. Okay. All right. And so with that, let's go ahead and jump into boundary value problems. Okay. Because if you are going to be setting up a problem in ANSYS, you need to kind of understand what are the essential parts that go into it. Okay. So every finite element problem, or every problem that we're going to be tackling in ANSYS, we can characterize it as a boundary value problem as well. Okay, so you can think of the boundary value problem as kind of the mathematical formulation or the mathematical expression of a typical finite element simulation. Okay. So as you're kind of setting up these finite element simulations, it's always useful to think about the boundary value problem that's existing kind of underneath all of that. Okay. Because like I mentioned, before that when you're using finite elements, you're using ANSYS, your the way you think about the problem is going to be different. Instead of solving a problem that's given to you, you are going to have to be you're more responsible of taking a problem that you're having and translating that into something that the computer can actually solve. And so in that sense, it's always good to think about if you want to use ANSYS for a problem, it's good to think about and write down what the underlying boundary value problem is going to be. All right. And so for boundary value, there's really kind of just three components to know. Okay. The first is your domain. So the domain is another name that what we call for the geometry. So it basically defines where and what we want to solve our equation on. So for the most part in this class, our domain is going to be defined by the CAD file that we import into ANSYS, right? So the CAD file defines the geometry on which we're going to solve it. Okay. So a little bit of terminology. And so, for a typical boundary value problem, so let's say that we have our generic domain like this, right? So let's say that our domain in this case is shaped like a potato. Okay. So the domain itself is usually given the symbol omega. And the boundary of the domain is usually defined as this kind of partial omega there. Okay? That's just kind of the notation that's typically used in textbooks and scientific papers. Okay. So we're not going to be using this notation all too much in this class. I'll typically refer to the boundary as the boundary, but just for your own, if you do end up kind of reading a bit more, this is kind of the terminology and the convention that's typically used. Okay. Okay. So, this may seem like the most obvious part of a boundary value problem, and it's not the part that people think about, but it is always good to think about, what is an appropriate domain? What is an appropriate geometry for the question that I'm trying to answer with my simulation? Because sometimes, it may not be obvious, and your choice of domain and your choice of geometry often has a big impact in terms of, how much you can do with the simulation just because of the limitations we have with the computers and the software here. But it also has a big impact on the cost as well, right? So I'll give you an example. So this was several years ago, and so I think it's safe to kind of tell this story because that student is long gone. But for a student's final project, they were interested in simulating basically a workout station at a gym. Specifically, they were looking at one very particular machine, which was seated rows. Okay, so I'm not going to try to draw it, but for those of you that go to the gym, probably what a seated row machine looks like. Okay, and so what they found, or what they wanted to do, was they wanted to analyze it in terms of the structural strength of the hand. Okay. Now, what they found, and so they did a little bit of searching online, and so they found a CAD model online of an entire seated row machine. And so kind of naively, what they did was they kind of took that CAD file, they imported into ANSYS, and they tried to run an analysis on that. And they were having a hell of a time trying to mesh it because just of the complexity of the geometry. Right? So then the student comes to me, and then he kind of describes kind of everything that's going on, and it kind of came from a perspective of professor, I'm getting these error messages in ANSYS when I'm trying to mesh, and so I'm not really quite sure what to do. And so I kind of rephrased the question to him and said, like what aspects of this machine are you actually interested in analyzing? And so then we kind of talked it through. It's like, we're actually only really interested in the load-bearing components. And so basically only the components of the machine that are going to be under stress when someone's trying to do a seated row. And so it's not really necessary for us to model up or have part of our domain all of the other components that are not going to contribute to that load-bearing portion. All that's going to do is it's just going to add complexity to your simulation. It's going to add a lot of dead space to your simulation. Things that the simulation has to mesh just because that's a requirement, but that mesh isn't going to be doing anything. And so it's just adding cost and complexity for almost nothing, right? And so through that, we were able to kind of extract just the components that he needs, and he had a much easier time to run the simulation from there. Okay. And so a lot of times, what may seem like an obvious question in terms of, what's your domain, what's your geometry, when you think about it from a perspective of, I want to run a simulation on this in ANSYS in finite elements, and every portion that I include in the CAD file is going to be simulated, then the question kind of rephrases itself, in an interesting way. Because you think about, what's actually necessary for me to do this analysis. And again, the answer may not always be obvious because a lot of times when you do create a CAD file, right? So probably what you guys are accustomed to if you've taken the SolidWorks course is that you're creating a CAD file to showcase all of the different geometrical features of your project, right? And a lot of times you're doing that so that you can eventually machine the part, manufacture the part, right? But when you import a geometry, when you import a CAD file into ANSYS, you're kind of answering a very different question, or I should say, you're using it for a very different application. And so usually not every aspect of your geometry is going to be important or necessary to run an FEA simulation. Okay. So one thing I want you guys to keep in mind, especially as we start to do our activities and once we start to get more into the meshing, is to think about, if you are going to be using a CAD file, what parts of this are actually going to be necessary for us to do this analysis. Okay. All right, so the domain is the first component of a boundary value problem, and there's already kind of a lot of interesting questions for us to answer here. Okay. Okay, any questions on this? Okay. All right, so the next part, or the next component of a boundary value problem is your governing equations. All right, so the governing equations basically are going to define not only the type of behavior, physical behavior that you're going to expect from your system, but also what kinds of outputs that you can expect from your simulation results as well. So there are lots of different types of equations that are out there. And one nice thing about ANSYS is that it expresses this, or it shows this to you in a very kind of intuitive way, right? And the way that ANSYS kind of shows this to you is that it tells you to kind of choose the relevant physics for your situation. So some examples that we're going to see in ANSYS, and so the one that we're going to use most commonly in ANSYS is a module or a feature package called static structural. Okay. So from that package there, you can see that we're solving these structural equations, and we're solving it in a static context. And so we're going to solve it for a situation that's not going to change with time. Okay. All right, another type of analysis we can run is steady state thermal. Right, so let's say that we're expecting some kind of heat transfer, some energy transfer to occur, right? So we can solve the heat equations through that steady state thermal. All right, another one is called explicit dynamics. Right, and so if you're expecting any kind of movement in your simulation, any kind of dynamic movement, there is a package for that as well. So I believe that's going to be activity 5, and so that might be the last graded activity that we do at the end of the summer session. So there is a way to do motion. Motion is very expensive, and so we're not going to use it too much, but it's still good to know kind of how to use it. Okay, and there's going to be lots of other types of examples as well. Right. So when we open up ANSYS, for our first activity, you'll see kind of all the different types of physics that are going to be there. Okay. So what you need to do is that when you're forming your boundary value problem is you need to ask yourself what physics are going to be relevant for my situation. Sometimes it's very simple. Sometimes it's just a single type of physics that we're going to be expecting. So those are kind of the best situations. In the fact that we only have to solve one type of equation. It ends up being very, very simple to. Okay, good. I'll test it out.
Okay, I just fixed it, so it should be good.
Okay, excellent. So good. Answer should be good, but I'll test it today, and then if it's all good, we'll do it tomorrow. Okay. Okay, so the first activity that we're going to do should be, we'll be in this category here. We'll have just kind of one type of physics to do, and that makes our solution very simple. But there are a lot of very interesting problems where we're actually going to combine multiple types of physics together. And ANSYS actually gives you a very elegant, very easy way to combine that. So I will say we're not gonna try it too much in this class. You may get a chance to do that on your final project, but ANSYS has a very kind of intuitive way to combine different physics. Let me give you an example. Okay. So again, this was also a final project of a student group. This one maybe I think 2 years ago, and so they were interested in simulating the physics of the brake rotor in their car. Right, so this one I can draw because the geometry for this is a little bit simpler. Okay, so basically they have this disk. Okay, and basically the idea is that this disk when the car was braking was going to be pinched with the brake pads at this location here. Okay. And so the simulation or the situation that they were trying to simulate was, as the brake pad kind of pinches on the rotor here, it's going to generate heat. Because basically all the kinetic energy that the car had as it was in motion, right, that needs to be dissipated so the car can come to a stop. So that energy has to go somewhere. And so that energy is generated as heat due to the friction between the brake pad and the rotor. Okay. And so first thing that they knew that they would have to do is that they would have to include some thermal aspect to their simulation. Right, so the heat equation was one type of physics that they knew they had to include. Okay? But what they were interested in is that as the brake rotor heats up, right? So as it kind of absorbs this heat from the brake pad, they're interested in seeing, how does the material properties, how does the structure of the brake pad change as a function of time? Okay. Right, and mechanical strength is governed by our structural equations. So they also had to solve the equations for structural mechanics at the same time as the heat equation. Right, so we have a two physics type systems here. So we have a thermal and a structural type simulation. Right, but they weren't done yet, just because they just wanted to add as much as they could. Okay. What they also said is that as the car was moving, right, this rotor is also going to be cooled by air, just because air is going to be flowing past it. Right? Because I think what happened was that they ran the simulation and then they found that if they didn't add the air cooling, then the rotor would just melt just because the heat had nowhere to go. And so they had to offload that heat somewhere. And so they had to add fluids to their simulation in order to get that going. Okay. So air is a fluid, right? And so as the air kind of interacts with the rotor as it goes around it, then we need to solve the fluid mechanics equations as well. And so it very quickly became a very complicated situation. So this is not a typical project. This is not what I expect for the final project. I just thought it was a very cool example, and they did it, and these student did a very good job. But you can see we're solving three types of physics all at the same time. So heat, fluids, and structures together. Okay, and ANSYS does give you the ability to do this. But this is just, I bring this up just to kind of give you a sense of, to think about, what are all the relevant physics, what are all the relevant mechanics that are going to go into the phenomenon that you're trying to simulate. Okay. So again, for the majority of cases that you're going to look at, it's going to be a single physics type system. Okay. But if there are multiple types of physics going on, you need to make sure that you account for that. Otherwise, you're not going to get the full picture in terms of your simulation results. Okay. Good. Any questions on that? Okay, good. And even within kind of the broader types of physics here, there are variations as well, right? So for structural mechanics, we'll talk later on in the session. There is a linear version of it and a nonlinear version of that, depending on the magnitude of deformation that you are going to be expecting. Okay. So there's lots of different variations. And I think once you kind of see the full list of physics that are available in ANSYS, it seems intimidating at first, but it's kind of more of a game in terms of trying to find what you need for your particular job. Okay, so governing equations is the second aspect of a boundary value problem that we need to know. The last aspect is also something that you need to specify kind of explicitly when you run an FEA simulation, which are the boundary conditions. Okay. So just like the name implies, boundary conditions are the conditions that we specify at the boundaries of our domain. Okay. More specifically, any kind of external effect that is going to be affecting the behavior of our system, we need to incorporate that somehow into the boundary conditions. So for example, some boundary conditions, that we're going to see very common in this class, one of those being what's called a fixed constraint. So a fixed constraint is what you're going to apply to certain aspects or certain areas of your geometry that are not going to move. Okay, so let's say that your part or your system is being attached to a bigger system, right? So that's where we're going to apply our fixed constraint. Okay. Right, so we'll talk about this a bit when we dive more to boundary conditions. But for most simulations, or for all simulations, you need to have at least one fixed constraint in your system. Okay, so that prevents basically rigid body motion. Okay. Another very common boundary condition that we're going to be applying is some kind of external force or external pressure. And obviously, for these boundary conditions, these are specifically for structures, right? So if you're going to be running a thermal simulation or a fluid simulation, your boundary conditions are going to be different as well. Okay. But any kind of way that a force is going to be applied onto your system, we have to include that in the boundary conditions as well, because that's going to cause your part to deform. Okay. Okay. So one thing that you're going to have to do is, because for a lot of times when you're going to be looking at a physical system that you want to simulate, right? It's not going to be labeled in a way where it's not going to tell you explicitly apply a force of 1,000 newtons at this location, or apply a fixed constraint at this location. Okay, so your job as kind of an engineer, as using the FEA, is to kind of interpret a physical situation and think about what is the type of boundary condition that's going to best fit this physical phenomenon. Okay. Sometimes it'll be obvious, right? So sometimes it'll be pretty clear in terms of this is the type of boundary condition that needs to be put here, right? So a force is obviously a force, and it acts in this direction at this location. But sometimes it's not going to be obvious, right? And so sometimes you're going to have to do a little bit. You're going to have to assume a little bit. You're going to have to kind of approximate a little bit. And so it's a bit more of an art than a science at times to determine what the best boundary condition is for a certain situation. And it's one thing I've been trying to incorporate a bit more into this class in terms of how to determine that. But for a lot of our activities that we're going to do, and even for a lot of the projects that you're going to end up doing as well, I would say those are situations where the boundary conditions are more or less pretty clear, pretty obvious in terms of what you should do. Maybe not for your final projects, but there are situations where it is tough to determine what the boundary conditions are. Okay. But what you have to remember for now is that any external effect or any kind of external factor that's going to be influencing the behavior of your system, you're probably going to incorporate that as a boundary condition. And so at this point, it's more important just to account for everything rather than just to get the boundary condition in the right form. Because in reality, there's once you have included the effect, there are actually multiple different ways to incorporate that. Okay, but for now, it's more important to think about what are all the effects that are going to be present, and make sure that there's a boundary condition that accounts for each. Okay. Any questions on that? Yes.
So, as I was kind of thinking about it, like, you mentioned like minimal, like you mentioned like flux and stuff like that. Typically, when we do like FEA stuff, does that kind of also like over like magnetism stuff? So like if you have a power line.
Oh yeah.
Oh,
Yeah. So electricity and magnetism also is governed by a differential equation, so you can solve for that as well. I would say it's typically not as common for mechanical engineers to do that, but ANSYS actually does have the capability as well. Yeah, so as long as your behavior is governed by differential equation, you can solve for it using FEA. And if it's not explicitly implemented in ANSYS, you can always write your own code to do that. Any other questions on this here? Okay, all right. So as we kind of do our ANSYS activity, looks like it's going to be tomorrow. So I want you guys to think about these things. And so, for some of the activity, just because it'll be the first one, I'll be a bit more explicit in terms of, this is the domain. This is the governing equation. We're solving a static structure. These are the boundary conditions. But, I want you guys to kind of think about this in the back of your head, because these are aspects that are going to be present for every FEA simulation that you're going to do. Okay. So that's it for that set of lecture notes. And so the other one I wanted to go over today, where we start, is kind of a review of solid mechanics, okay? Or strength of material. That's kind of how I learned from. Okay, so a little bit kind of a big shift. So in a normal semester, this would take place on a different day than kind of what we just discussed now. But with a 3-hour session, we kind of have to cover it on the same day. So this is, we're shifting from FEA to kind of more solid mechanics. Okay, but I did want to cover this, and this is kind of good to kind of go over before our first activity, because tomorrow we're going to be simulating basically the first ANSYS simulation that everyone runs is a plate in tension with a hole in the middle, right? And so there's going to be concepts of tension, compression, stress, strain, failure, factor of safety, and so I want to make sure that we're all kind of on the same page of that. If anything, this should hopefully just be a refresher that if this is just a refresher and it's boring, that's great. Then pick up a lot and so on. Okay. All right. So first, let's go over the concept of a stress. Okay. Well, let me say this first. Right. So when we talk about strength of materials, right? When we talk about solid mechanics, we're explicitly thinking about structures or geometries that have forces and loads being applied to them. Right, so I think every one of our ANSYS activities are going to do that. Okay. Now, like I mentioned, that's not the only thing FEA can do. FEA can also do thermal simulations, fluid simulations, electromagnetism. But just because of the nature of where this class kind of is in our curriculum and the nature of our prerequisites, we're going to focus mostly on the structural component. Okay. So structures that are subjected to forces and loads. Basically, a few things are going to happen in those situations. And so on the one hand, when you apply a force to an object, and the object, stays relatively still, it tends to deform. Well, and of course, that's assuming that there's going to be no rigid body motion that takes place, right? So the object is not going to be traveling anywhere. So, we're looking at just pure static structures, right? And of course, we're also going to assume that there's going to be no, the part is not going to fail as well, right? So the part is also going to stay, we're not going to stress to the point where, we're going to have plastic deformation and fatigue.
Is that a setting or does the system just normally do that?
It depends on the magnitude of force that you apply. And so if you apply just a moderate amount of force, there's just going to have light deformation. But if you increase the amount of force, the whole thing's going to break.
The simulation will actually show that though?
If you push it up, yeah.
Oh.
Yeah. For those ones, you'll have to include nonlinear dynamics because you need plastic deformation basically. And so our initial simulation will just be linear. And so actually, if you keep pushing it, then the entire structure will keep deforming. But at a certain point, you'll start to say, okay, the structure is not going to, it's not made of rubber, so it's not going to stretch this much.
Makes sense.
So the structure will deform when you do expose it to those forces. The other thing that's going to happen is that there's going to be stresses that develop internally within the structure as well. And so actually to answer your question a bit more, so even if we're just looking at a pure linear situation where the part will just keep deforming, you can actually tell from the stresses that, you know, this is not going to be realistic because the stresses that you're going to see are going to be way past the breaking point or the yield limit of the material.
That makes sense.
So we're going to review just a few concepts regarding this, just to kind of give our activity a bit of context for tomorrow. Okay, so let's start with stresses. Okay. So a stress is essentially a force. Well, the pure definition of a stress is just a force that's distributed over an area. And stress is developed, the reason stress is developed within a structure is to make sure that every single part of that structure remains in static equilibrium. Okay. So let's go ahead and look at a very simple case here. Okay, so you've probably seen this before. This is probably kind of one of the first examples that you see in solid mechanics. So let's look at a simple rod in tension. Okay, so if we have a rod here, right? So it's kind of a slender structure, and we apply an equal and opposite force on both sides. So let's say we apply a force T going to the right on the right side, and an equal and opposite force on the left side, right? So if you sum up the forces on the structure, all the forces are going to equal 0, okay? So there's going to be no motion, right? So there's no acceleration. But, you know, we know that this rod here is going to deform, right? And so, you know, granted that the amount of tension that we apply is not too severe, so let's say it's fairly moderate, we expect this rod to elongate slightly. Right? And so as a result, I can use yellow, right? We expect this rod to elongate slightly, maybe thin out a bit, kind of near the Okay, so these are the types of situations we're going to be looking at, although not nearly as simple as this, right? So there's no point in running a simulation on a rod in tension, but you know the same idea where we have kind of forces applied onto an object, and the object is going to deform in some way, while the overall structure is going to remain static. So there's going to be no dynamic or rigid body motion. Okay, so if we take the structure, right? And let's say that we look at a cross section. So let's make an imaginary slice kind of down the middle of this rod. Right, so if we take that slice, so let's say we take the left portion of this rod and we draw a free body diagram. We look at just this portion here. Okay. So we've included the left end of the rod. So there's going to be a tensile force going to the left. Okay. Okay. But you know what we're saying is that, you know, this slice here, you know, even though we're not looking at the entire rod, right? We know that this slice here is part of our original rod. So this slice here should also be in static equilibrium as well. So in order to maintain that, there has to be an equal and opposite force that is on that slice that opposes the external tension. So there has to be an opposing force that opposes that tension. And what develops here is our stress, right? So what we know from solid mechanics is that there's a stress that develops kind of on the interior of the rod there, okay? Which typically we call sigma. So that stress is what develops internally so that this particular portion of our rod does maintain that static equilibrium. Right, so the sigma here is the stress, where in order to maintain static equilibrium, the stress here has to have the value of the tensile force T divided by A, where A there is the cross-sectional area of the rod. Okay, so that's the idea with stress, right? And so in order to maintain equilibrium at every single portion, at every single slice of our structure, right, these stresses have to develop. Otherwise, you know, our structure would just kind of break apart. Okay. Okay. So when we run the simulation tomorrow in ANSYS, you know, one of the primary outputs that we're going to look at is the stress distribution. Okay. And there's a lot that we can glean from that stress distribution, because that's going to tell us, you know, what are the areas that are at risk of failing. That's going to inform our factor of safety, things like that. Okay. All right. And so what you should also remember from solid mechanics is that there are multiple types of stresses, at least in terms of direction. On the one hand, we have normal stresses. So normal stresses are kind of what's illustrated above. So normal stresses act perpendicular to whatever surface that we are considering. And so normal stress, you know, would look something like this. Right, so let's say we make a cut plane like that. Any stress that is pointing in the direction perpendicular to that cut plane is a normal stress. Okay. So normal stresses are very common, and so you know usually when you subject your structure to any kind of tensile or compressive force or bending force, it's primarily going to be normal stresses that are going to develop. Okay. The other type of stress is a shear stress. So a shear stress is defined as any stress that acts parallel to a cut plane or surface. Okay. And so to kind of illustrate that, let's say we have a structure like this. Okay. A shear stress is going to act parallel to whatever plane that we have. Right? Right. So typically, you know, if you're designing an engineering system, you want to avoid shear stresses because you know for a lot of very common engineering materials, you know, I want to generalize that even more. But most materials are going to be much weaker in shear than they are in normal stress. Okay. So if you have a relatively well-defined engineering system, hopefully you're not going to see too much shear, but it is something to consider and kind of be aware of that. If you do see a large amount of shear, that might be a risk factor that you have to consider for your. Okay. Okay, but for most everything in this class, we are going to be looking at normal stresses for the most part. All right, any questions on this? Yes.
Yeah, so when you said most engineering materials, are you talking about like composites or just in general like that?
Just in general. So I would say for most materials, they're going to be weaker. Their shear modulus is going to be much weaker than their typical yield strength. Yeah, most engineering materials are designed to be in tension or compression. Okay, good. All right, and so with that, let's see, just in the interest of time, let's go over the idea of the equivalent stress now. Okay. So, kind of what we've discussed so far is kind of just like the basics of stress, right? So you have a structure that's exposed to forces, and a stress has to develop in order to keep the structure in equilibrium. Okay. In reality, stress is actually a very complex mathematical concept. Stress is not just a scalar; it's actually a what we call a tensor quantity. Right? And so a tensor quantity basically means that we express the stress as a matrix. Okay, it goes beyond a vector, right? And so I would say a lot of variables and a lot of concepts that you've probably learned in terms of displacement, velocity, forces. Those are all vector quantities, right? Stress actually goes one step further than that and expresses it as a matrix. Okay? And so mathematically, if you were to look at the stress, okay, at any given location. Right? At any given location, we can define the stress as this 3x3 matrix. And so it has 9 components. We have sigma xx, sigma yy, sigma zz, and then we have the shear stresses, which is tau xy, tau xz, xy twice, tau yz. Okay. And the whole thing is symmetric, right? So all the shear stresses are symmetric across the main diagonal, right? And so if you wanted kind of a full picture of the stresses, this is kind of what you would express, okay? But in reality, something like this is very kind of cumbersome to kind of express, okay? So this tensor here, this matrix, this matrix expresses all of the different components of the stress as well as all their different directions. Right? So we have normal stresses in the x direction, y direction, z direction, and then shear stresses in all the different directions as well. And there are ways to extract this as well, right? And so if you're really interested in all of the different components of stress from an ANSYS simulation, there are ways to kind of pull this out. And if you're doing a very tight, very kind of precise engineering design, that may be necessary, right? If you're designing against the specific components of stress. But I would say for the most part, for most, I would say kind of practical situations, this is kind of a little bit too much information for us. It's a little bit too cumbersome to kind of work with from a practical perspective. And so it would be nice, if we were looking at a particular structure to just look at the magnitude of the stress, okay? Because, if we think about it, right, if we think about forces, right, we usually, when we think of forces and loads, we don't really think about the separate vector components of the force, right? So we don't think about the x component, the y component, the z component of the force. We just look at the magnitude of the force in terms of how much force is being expressed, okay? Now, the magnitude of a tensor gets a bit complicated. There's no kind of explicit formula that expresses the magnitude of a matrix or tensor quantity. And so specifically for stresses, there's this concept of an equivalent or von Mises stress that we can express as an alternative. Right. So something like the von Mises stress is usually very useful for us from a finite element perspective. Because, a lot of times, when we're running an FEA, when we're running a simulation, we're kind of asking kind of more high level questions in terms of, is our part going to break? What are the magnitudes of the stresses, right? We're usually, kind of discovering and kind of computing each component of the stress is a little bit too nitty gritty for kind of a high level question like that. Okay. So the von Mises stress is the typical stress that we're going to express when we run a finite element simulation. Okay, there is a formula for it, which I always forget to write down, so I'm just going to look it up kind of very quickly. Okay. But basically, it's going to be a combination of all the different components of the stress. I started typing up von Mises stress in Google, and it gave me the link to Von Miller, which is a football player. Okay, so the von Mises stress, the formula for that is the following. Okay. So you don't really need to know this formula. It's just useful to know in terms of how the von Mises stress is related to the stress components. But, it is useful to know. Okay. All right, so the square root of 1/2. We have the difference of all of the normal components of stress. And so we have sigma xx minus sigma yy quantity squared plus sigma yy minus sigma zz quantity squared plus sigma zz minus sigma xx quantity squared. Okay. So we're basically taking the difference between all the different normal stress components, okay, and squaring them together, and then we add all the shear components as well. Add.
Listen to 3 times.
Okay. We add 6 times the shear components of tau xy squared, tau xz squared, tau yz squared. And so all that is under the square. All that is under the square. Okay. So again, this is a formula here that we're never going to plug into or use in any calculation for this class. But the idea is that we're taking all of the components of stress. Right, so we're plugging into a formula like this, and then what we're obtaining at the end, okay, is one single scalar value for the stress, which is essentially the magnitude of the stress that we're going to be using. Right, so that's kind of the benefit. That's kind of the purpose of why we compute this von Mises stress is that, instead of looking at all of the different components of stress, which, you can do, right? I say it's cumbersome, but it's not like it's impossible. But, usually something like the von Mises stress is a little bit more convenient to express, right? Especially when you're writing technical reports, you're kind of communicating your simulation results. Usually it's kind of more, I would say it's a bit more expected nowadays to kind of just have a single figure for your stress. And if you're going to show just a single figure, the von Mises is typically the best figure to kind of express for that. Okay. All right. Any question on the von Mises stress? Okay. So the von Mises stress also has another application. So we won't see this in activity 1, but we will do this in activity 2 probably next Tuesday. Okay. The von Mises can be used to predict whether a part or whether a structure is going to fail under a given load. So that's what's known as the von Mises failure criteria. Okay. So we're going to talk more about kind of stress-strain relationships in a little bit, but for this part, you should know that, at any given point for any material, there is a maximum amount of stress that it can withstand before the entire material just breaks apart. Okay. And so, we kind of understand that kind of anecdotally as well, right? So you take a structure, like you take this pen, right? If you apply enough force to this pen, the pen is eventually going to break, right? Because it's the material that the pen is made out of can only withstand a certain amount of forces, okay? So mathematically, the way that we predict that is through failure criteria. So every material has a certain amount of yield strength, which you can interpret as the maximum amount of stress that it can withstand before it will start to fail. Okay, so one thing, one very common kind of use for finite elements is to determine, whether your part is going to fail or not if you're going to expose it to these certain forces. Okay. Now, naively, kind of the simplest way that you can determine that is you can run your simulation, you can expose it to forces, and you can check to make sure if the equivalent stress is equal to, or as long as the equivalent stress stays below the yield strength at every location within your structure, then your structure will be good. It's not going to fail. All right, so one thing we're going to be doing in activity 2 is we're going to be running a simulation. We're going to check the equivalent stress, and we're going to compare that to the yield strength. okay? And then based on that, we're going to make a statement of whether or not we expect this part or the structure to fail or not, okay? Now, this is a very simplified way of looking at it, right? So in reality, in between, our structure, being good and our structure failing, there's a lot of complex kind of deformation that occurs along that way, right? So we're kind of completely ignoring the fact of plastic deformation, right? So I wouldn't say this is the most, I would say, elegant way to kind of compute this, but it's always good to kind of give you a good ballpark estimate, okay? Because a lot of times, you're designing a structure for the first time, right? You're really not sure if the structure is going to survive or not, right? Using this von Mises failure criterion will give you a sense of, okay, we're way off, or maybe we're pretty close, or maybe failure is not something we're worried about at all. Okay. And so, if you're on a borderline case of whether the part's going to fail or not, probably you need to include more physics, you need to include more plastic deformation, but the von Mises failure criterion is a good starting point, okay? And it's the one, just because of its simplicity, is the one we're going to use a lot in this class. Okay, any questions on this? Okay. All right, so last thing I want to go over before we head out is the concept of strain, as well as its relationship to stress. Okay. So strain, probably as you know, is a way to express how a structure is going to deform in response to external loads, right? So we've discussed kind of the force response, right? So stress expresses the force response that a structure must undergo in order to maintain a static equilibrium. But the deformation that it undergoes as well is often expressed as strain. Okay. So strain is a very interesting quantity because it's unitless, right? And so it doesn't have any units. And so it's expressed as kind of you can think of it as kind of like a relative change in terms of the new deformed geometry relative to its undeformed geometry. Therefore, it is units. Okay. All right. So I think the most simple definition for the strain is to use just a one-dimensional case. Although strain is kind of extrapolated for 2 dimensions and 3 dimensions as well. Okay. But I think the way that is first expressed is, let's say that you have a one-dimensional rod. Okay. Your rod here is fixed against the wall, and then we apply a force to it. Right. So as a response, we know that this rod is going to deform. Right, and so in this case, we do expect the rod to lengthen in response to the applied load. Right, so let's say it lengthens by an amount delta L. Okay, so what we say is the strain, or epsilon, is equal to the change in length delta L divided by L, which was the original length. And so you can see here that both quantities there have the same units, and so they both have units of length, right? And so we take the ratio and then we get a unitless quantity. Okay? But that unitless quantity is expression of the ratio of the change versus the original geometry. Okay. All right. So stress and strain in a material are intricately related. Okay? And so you can't have one without the other, right? And so if you have strain, that means you have stress. And if you have stress, that means you have strain, right? Now, the exact mathematical relationship between stress and strain will depend on the type of material that you're looking at, okay? So some materials have a very simple linear relationship between stress and strain. Some materials have a complex kind of nonlinear relationship. Those are more nonlinear materials. And even for very simple materials, the stress strain relationship changes depending on the amount of strain that you have as well. Okay? But in a very simple case, so for very simple linear materials, so these are very simple materials like your metals, right? Mostly metals, right? Okay, so this is probably the first kind of equation that you've learned in solid mechanics, which is that stress in a material is equal to the Young's modulus E multiplied by the strain. This E, of course, this is what we call the Young's. And accompanying this, you've probably seen this plot before as well. So on the horizontal axis, we have strain. On the vertical axis, we have stress. Okay. And the relationship between them is linear. Okay. Okay. Where the slope of the line is the Young's modulus. Okay. Okay. So that stress strain relationship tells you, for a given amount of strain, we're going to have a certain amount of stress as well. Okay. Okay. And so I bring this up just to kind of define the Young's modulus a bit better. So this is a very key material property. Right? So aluminum is going to have a certain Young's modulus, which is going to be different than steel, which is going to be different than balsa wood, which is going to be different than rubber. Okay. So depending on the material that we're using for the simulation, we need to define the Young's modulus appropriately. Okay. So what does it represent? The Young's modulus represents basically how stiff the material is, okay, or how resistant it is to deformation. So visually, you can see that as the Young's modulus changes, it's going to change the slope of that line. Okay. But I think physically, intuitively, you can think that the way I always think about it is as the stronger the material is, or the more stiff the material is, the higher the Young's modulus is going to be. All right, so that's kind of an important point to kind of note here, right? And I always think about it like this, right? So the stress, kind of like as we've discussed here, is kind of a function of the external force. And so the more force or more external force that you apply to a structure, the higher amount of stress is going to develop. Okay. So let's compare this, right? So let's consider this kind of black line right here as kind of our baseline material. Okay. If we compare that to a material that is stiffer, right? Okay, so a stiffer material, what we're saying has a higher Young's modulus. Right, so higher Young's modulus means the slope of that line is going to be increased as well. Okay. And so if we kind of compare, right? So let's say that we compare our two curves here at a certain location. Okay. So let's compare it at this location here. So let's go ahead and trace a line downwards, just like that. Right. So what we can say is that in order to get this amount of strain, or in other words, in order to get this amount of deformation for the stiffer material, we need to have a higher amount of stress, right? I apologize. I thought that word there was going to be shorter, so I would have given myself more room. Okay. And so if the stiffer material requires more stress, that means it requires more force as well, right? Right. And so in that kind of tracks in our mind, right? So one comparison that we'll see in activity 1, we're going to use steel as our material. Well, for activity 2 that we're going to do next week, we're going to use aluminum. And steel, as most of us know, is stronger than aluminum, right? And so in order to get the same amount of deformation in steel, you need to apply a much larger amount of force, right? And that's expressed by the fact that steel has a higher Young's modulus. Okay. Okay. So, Young's modulus is a very important material property. We're going to be kind of, using it a lot in our simulations. And so it's good to kind of understand what it represents for these, for these materials and for these situations. Okay. All right. Any questions on this? Okay. All right. So there's a couple more points I do want to make on mechanics, but we are out of time. And so I'll save that for tomorrow. And so when we come back tomorrow, I'm gonna test the ANSYS just to make sure that it works. I know Lorenzo came by and he tested it, but I want to just make sure for myself. Right. So when we come back first thing tomorrow, we will do our first ANSYS activity. That'll take us about half our time, and then from there we'll continue on with you. Okay. But thank you guys for coming today. It was great meeting you all. Hope you have a good rest of your evening. I will see you guys all tomorrow. Yeah, same as we did for food. I think I tried to do it, so whatever you do for the ANSYS study and I might be. I might be really good. I said, the third job of which is sitting there, I should have minded. So you went to this website? Oh, I'm sorry. Yeah. So the one on the stove is out of date. So I'll send an announcement. Say you can download as a student. Okay. Yeah. So it should be 2026. Yeah.
You have a free day. Oh, wait, but
Raise your new Monday.
That's like
That's
oh, yeah.
it's not like that.
Yes, it's a little lower.
Yeah,
On the curve. Yeah. But.
Yeah. Yeah.